Section 1.2.4 Load Balancing, Traffic Flow and Distribution. When people first step into the cloud world, they usually picture very visible things. Virtual machines, databases, containers, Kubernetes clusters, serverless functions quietly spinning somewhere in the background. Those are the parts you can see, provision, and scale with a few clicks. But there's something much less visible that quietly decides whether any of that actually works in real life. Load balancing. Without it, even a well-designed system can fall apart faster than you'd expect. Think of a city with modern roads, good planning, and solid infrastructure, but only one bridge connecting it to the outside world. Everything looks fine until traffic spikes, then nothing moves, and suddenly all those nice design decisions stop mattering. That's what happens to cloud systems without proper load balancing. A simple way to think about this is to imagine the cloud as a huge highway network. A virtual private cloud, a VPC, is your private slice of that network. It's isolated, it's secure, it's yours. Inside it, subnets act like lanes and exits, shaping how traffic flows and where it's allowed to go. And right in the middle of all that sits the load balancer. It doesn't generate traffic. It doesn't run your business logic. What it does is decide where traffic goes. And that decision turns out to be far more important than most people realize at first. The load balancer constantly looks at incoming requests and makes judgment calls in real time. Which backend is alive? Which one is overloaded? Which path still makes sense right now? When this works well, you barely notice it. When it doesn't, everything else starts to crack. This isn't something you add later. If you get load balancing wrong, the rest of your architecture doesn't really get a chance to shine. And this is where interviews quietly raise the bar. Above the junior level, nobody explicitly asks, "Will you use a load balancer?" It's assumed. What they're really testing is whether you understand why it's there and what happens when things go wrong. One thing that's worth clearing up early: load balancing isn't magic. The cloud doesn't do it for you automatically, just because you click the right service. Someone still has to configure it, monitor it, and adjust it when reality doesn't match assumptions. Another common misconception is that load balancing is only about websites. It's not. It applies to APIs, microservices, internal service calls, databases, and even protocols that have nothing to do with HTTP. When it's misconfigured, problems tend to show up in ugly ways. Uneven load, cascading failures, or subtle security issues that only surface much later. When it's done right, the system feels calm, almost boring. And that's usually a good sign. To make sense of load balancing without drowning in terminology, it helps to think in layers. But don't worry about memorizing names. At the lowest level, there's transport-level load balancing, often called Layer 4. This works with TCP and UDP. TCP is careful. It confirms delivery, retries when things go wrong, and keeps connections orderly. UDP is much looser. It's fast, lightweight, and doesn't wait around for confirmations. That's exactly why it's used for things like voice, video, and gaming, where speed matters more than perfection. The key idea here is simple. Layer 4 load balancers move traffic quickly without really caring what's inside the packets. Above that, there's application-level load balancing, Layer 7. This is where the load balancer actually understands what the traffic means. It can look at URLs, host names, headers, cookies, and make routing decisions based on that information. This is where modern microservice architectures start to feel flexible instead of fragile. Then there's global load balancing, usually built on DNS and Anycast. This layer doesn't touch individual connections at all. It simply nudges users toward the closest or healthiest region. You'll often see all of these combined in real systems. Global routing gets users to the right place on the planet. Then regional load balancers handle distribution locally. One thing that trips people up in interviews is assuming Layer 7 is always better. It isn't. It's smarter, but it's also heavier. Layer 4 is faster and works naturally with non-HTTP traffic. The right choice depends on latency, protocol, and failure modes, not on which option sounds more advanced. Now let's make this concrete with AWS, since it still dominates many production environments. In practice, you'll run into three main load balancers. The application load balancer, ALB, is the one that thinks. It's built for HTTP and HTTPS. It understands routing rules, paths, and headers. It plays very nicely with containers, CI/CD pipelines, and microservices. Features like header and URL rewriting make it useful for migrations, A/B testing, and gradual rollouts. The network load balancer, NLB, is the one that moves traffic fast. It operates at layer 4, preserves client IP addresses natively, and provides static IPs. That alone makes it essential in regulated or legacy environments. By 2025, it also supports quick and weighted target groups, which allow you to shift traffic unevenly based on backend capacity. That detail is more important than it sounds. Weighted routing lets you roll out changes safely, compensate for uneven hardware, and avoid pushing fragile systems too hard. Exactly the kind of trade-off interviewers like to hear explained clearly. The Gateway Load Balancer, GWLB, is different. It doesn't route traffic to applications at all. It transparently inserts security appliances, firewalls, inspection systems, intrusion detection, directly into the traffic path. In compliance-heavy environments, this is non-negotiable. If you want a simple mental shortcut that actually sticks, it's this. ALB thinks, NLB moves, GWLB watches. Behind every load balancer are target groups. These are the actual destinations for traffic: instances, containers, IP addresses, or serverless functions. This is usually where something clicks for beginners. Once you understand target groups, you stop thinking in terms of individual servers. You start thinking in terms of traffic paths. An application load balancer can route traffic to multiple target groups based on simple rules. Different paths go to different backends. Different host names go to different services. That's how companies like Shopify isolate admin traffic, push APIs to serverless platforms, and test new features on a small slice of users before committing fully. Netflix uses similar ideas to personalize content delivery at massive scale. One easy mistake here is forgetting that only healthy targets receive traffic. If health checks are misconfigured, some systems quietly sit idle, while others get hammered. How traffic is spread depends on distribution algorithms. Round-robin cycles through targets one by one. Least connections sends traffic where it's currently lightest. IP hashing keeps the same client pinned to the same backend. Weighted approaches deliberately send more traffic to stronger systems. Round-robin sounds fair. In production, fairness usually turns out to be an illusion. Health checks are what keep load balancing honest. They're small probes that constantly ask, "Are you still alive?" After enough failures, a backend is removed. When it recovers, it's brought back. On paper, this looks like a minor configuration detail. In real systems, it's one of the fastest ways to take everything down if you get it wrong. More than one high-profile outage has started with health checks that were just a little too aggressive. Sessions complicate things further. Sticky sessions can keep users on the same backend, but they're a compromise. Whenever possible, stateless services scale better and fail more gracefully. Client IP handling also matters more than people expect. ALBs pass client IPs through headers. NLBs preserve them directly. This affects logging, compliance, and fraud detection. Load balancers don't automatically hide client IPs. Assuming they do is a quiet but dangerous mistake. During deployments, connection draining lets in-flight requests finish before backends disappear. Without it, zero downtime quickly turns into wishful thinking. Security passes through load balancers as well. TLS termination simplifies certificate management and reduces backend load. In stricter environments, traffic is re-encrypted end-to-end. Newer platforms even support post-quantum cryptography. A surprisingly common oversight is forgetting mutual TLS for internal services. Advanced architectures often combine load balancers, a fast, static IP layer in front, smarter routing behind it, edge services on top for global reach and protection. Most load balancing failures come down to assumptions, assuming it prevents downtime on its own, assuming monitoring can wait, assuming back-end capacity will magically scale, and assuming costs will stay small if nobody looks at them. In DevOps culture, load balancing is baked in from day one. It's defined as code, validated in pipelines, used for canary deployments. By 2025, predictive scaling, quick, and security first designs are becoming the norm. And this brings us to the real interview signal. What stands out isn't knowing service names. It's being able to explain trade-offs. Why one layer makes sense here. Why another fails under pressure. And how real systems behave when traffic doesn't follow the happy path. Once traffic flows reliably, the next question naturally follows. Where does it go? That's where databases come in. Often sitting quietly behind load balancers in private subnets, relying on the very same principles of distribution, resilience, and control. End of section 1.2.4.